Test is on Monday. It's about 27 or 28 questions right now. There are some from OpenStax. I think I counted 8 or so questions from OpenStax, but they're similar to questions that we worked in class. They're not, the funky questions. And OpenStax, especially in the fluids chapter, there were lots of things where you had to do unit conversions and calculating areas, and you were dealing with diameters and all that. I try to minimize that as much as possible because, I just want to test you on the content that we're covering, not on can you calculate the area of a circle or whatever. But so just be aware of that as you're going through the OpenStax, that there are some hoops that you have to do there that you won't have to do on the exam. Oh, let's see. Just sort of a quick overview of what's on the exam, and then I'll address your questions. So Chapter 8, sort of our big chapter. It has all that stuff from all the way from energy, momentum, all those different topics, but in a rotational frame. So in Chapter 8, we have torques. We have where you have to find the net torque of things. You have moment of inertia. We have to find the moment of inertia for an individual particle and then also for rigid objects, and that sometimes comes up in individual questions. And we have Newton's second law. The sum of the torques is equal to I times alpha, where if I apply a torque to an object, I can calculate its moment of inertia and then calculate its angular acceleration. Several problems like that we did. We had energy, kinetic energy, both rotational and translational. Right, that translational, that's that 1/2 mv squared. We saw that in Chapter 5. Angular momentum, that's L equals I omega, and then more particularly that Li is equal to Lf. That angular momentum is always conserved, assuming that there are no external torques. All right, with solids and fluids, that's Chapter 9. I know this is fast, but I want to get to your questions as soon as possible, okay? But Chapter 9, the phases of matter. I think there was just one question about phases of matter. Just solid, liquids, gas. The elastic properties of solids, that's that F over A is equal to Y delta L over L. If I apply a strain, if I apply a stress to something, I cause a strain. Look back at some of the questions that we did in class on those. There will probably either a calculation, probably a calculation regarding that. Density and pressure. Our density is mass over volume. Our pressure is force over area. All right, we had some OpenStax questions. I think I pulled OpenStax for these. Density is mass over volume, and then pressure is force over area. But pressure comes up several times in this chapter, because we also do the pressure at a certain depth, and that was this deal where we did P is equal to P naught plus rho GH. Right? If I go to a certain depth in a liquid, I have a column sitting on top of that point, and the pressure due to that column is equal to rho times G times H. Pascal's principle, you're going to have a hydraulic system where you apply Pascal's principle. P1 is equal to P2. Look back at those, and we can work one if you want, a hydraulic system. You will have a hydraulic question. Pressure measurements, manometer, barometer. You will have a manometer or a barometer. I think just one, maybe 2 questions. And then Archimedes' principle, where you have to calculate the buoyant force, or maybe you calculate the volume that's being submerged, or you calculate maybe the depth of something that's being submerged. There was a question on OpenStax regarding apparent weight. Y'all did that in lab, but you will not be doing any apparent weight on the test. Is that clear? Okay. And then motion, that's the equation of continuity, A1V1 equals A2V2. That's based on the conservation of matter, that any matter that comes through one point has to go through the other point. And then the other is based on the conservation of energy. This is Bernoulli's equation, 1/2 rho V squared plus rho GH, that's kinetic and potential, plus pressure. This is equal to a constant value, conservation of energy. Okay, and then thermal physics, Chapter 10. Just a few questions from Chapter 10, 4 maybe, I think, not that many. temperature scales. Maybe 5 questions. Linear expansion and the ideal gas law. I would expect to see a combination of conceptual and calculation problems for those. Okay, so heavily on Chapter 8 and Chapter 9, and then just a few questions from Chapter 10. But really, Chapter 8, you haven't seen that in a while, so I would focus on that one. But Chapter 9 has a bunch of stuff in it, and it's all sort of interconnected, but it's also sort of separate silos. So being able to identify those questions and what principle they apply will be important for you. Okay, questions? Where? Second Rachel.
Fall 14 exam, number 12.
All right, fall 14, 12. I think there are 2 versions, so tell me if this isn't the right one. Huh? Thank you. Exam what? 4? From fall 14. Oh, this one? Your question is about the 3 kilogram mass? Why it doesn't contribute any moments of inertia? Is that what you wanted to know? Yeah. No. Whenever you see particles like this, if you see that word particles, like right here, we're just dealing with determining the moment of inertia of the particles. And to do that, we say I is equal to the sum of mr squared for each individual particle. So we just think of them as point masses. They don't have a radius. And because this mass is on the axis of rotation, it's right here, this thing rotates like this, right, around that axis of rotation. This one doesn't contribute anything to the moment of inertia because r is equal to 0. It is on the axis of rotation. So I only have 3 times 4 squared plus 3 times 4 squared. So that's 96. C should be the answer.
What is the 8 meters for?
That's the side. It's an equilateral triangle, and so this distance is 8 meters.
Isn't it above it says which side is it?
Oh, yeah, I should have changed that. I must have told them in class. Okay, so this would be 2 and 2. What was the right answer here? Okay, well, no, this is wrong then. This should be 8. And so this is 4 and 4. Okay? I just had a mistake. I'm sure I corrected it in class. Okay?
So you just have to find the moment of inertia.
Yeah, let me work it out just for it to be clear. So I'm only considering these 2 masses because for this one, r is equal to 0. So it's going to be 3 kilograms times r, which is 4 meters. That's not the radius of the object. It's the distance from the axis of rotation. It's like in torque, right? It's the moment arm. Times squared plus 3 kilograms times 4 meters squared. That's 48 plus 48. That's 96. Okay? All right, Rachel, you had a question?
It's not really specific. It's just that I don't understand
Nothing
nothing on chapter 9.
on chapter 9? Okay. Okay, well let's oh goodness. Let's address specific questions, and then if we need to, we can sit down, okay? Yeah.
Okay, quiz 5 from 2013, number 60.
You don't like it better when you call them quizzes? Like, it didn't really help that much. That I tried to make them seem less important, but they were still really important. So which one?
Quiz number 5. Oh,
What?
no,
60. Okay, so this is Bernoulli's principle, but it includes a change in height. We haven't done this, and you're not going to see a change in height, but you could see Bernoulli's principle. Let's go through it, but then I'll explain when I get there. So Bernoulli's principle says that 1/2 rho v squared plus rho gh plus the pressure is constant. That means it's equal to 1/2 rho v squared plus rho gh, that's a rho, plus the pressure, but that's all constant. Now it tells you that the pressure remains unchanged. So I'm just going to get rid of these because they're equal and I can subtract them from both sides. However, the height changes. So here h is equal to 0, but over here h is equal to 3. The pipe goes up, right? The pipe is traveling along like this, and then it goes up like that. And so the speed is going to change because some of the energy is going into potential energy. Okay, so I want to know what is the speed of the pipe on the second floor. It gives me the radius here, but you don't really need the radius. It's not important because I say 1/2 times rho, which is 1,000. That's given in the problem, but that's the density of water, times 15 squared plus 0, because h is equal to 0, is equal to 1/2 of 1,000 times v squared plus 1,000 times 10 times h, which is 3. This is the density of the water. This is the acceleration due to gravity, g, and then this is 3 meters, which is the height. And then you solve this for v. Okay? Can I leave you at that to solve it for v? We didn't do this where we have rho gh, but you can still see something. I didn't give any problems where I changed the height because we didn't work that in class. But I could give you a different velocity, say that the velocity increased, and then ask you what is the pressure change. Okay? What else? Any more from this one? No? All right. Questions? OpenStax questions? I know y'all have questions. Yeah, Mallory?
Number 2 on fall 16.
Number 2 on fall 16. This one right here?
Yes.
Okay, gosh, I always have to think about these. These always confuse me. Two objects have the same angular momentum. That means that L1 is equal to L2. So that means that I1 omega 1 is equal to I2 omega 2. That's what that says, that they have the same angular momentum. But object 1 is spinning twice as fast as object 2. All right, so this is omega 1 is twice omega 2. All right, so I could rewrite this and say I1 omega 1 equals I2 2 omega 1, right? Because omega 2 is, or excuse me, half omega 1. Okay, you with me on that? Omega 2 is equal to half of omega 1. If the energy of object 2 is 10 joules, what is the energy of object 1? If the second object has half the speed of the first object, that means that it's going to have twice the moment of inertia. Right? It's going slower, so it has twice the moment of inertia. So if I were to draw these, this would be 1, and this would be 2. It's bigger, it has twice the moment of inertia, so it's going slower. This is object number 1, object number 2. And I want to know what is the energy of object number 1. Well, look, object number 1 has half the moment of inertia of object number 2, but it has twice the speed of object number 1. It still has the same momentum, but it's proportioned differently because it has twice the speed but half the moment of inertia. Let me step back through that, okay? Because there's sort of a lot of thoughts that are going on. My angular momentums are the same. Angular momenta are the same for both objects. This one's spinning fast. This one's spinning slowly. All right? Because this one's spinning fast, it must have a small moment of inertia. Because this one's spinning slowly, it has a big moment of inertia. Because there's this trade-off between I and omega. So, the one that's spinning fast, because of this factor of 2, it's spinning twice as fast. It has twice the speed, but half the moment of inertia. So now, knowing that, we go and we talk about energy, 1/2 I omega squared. It has twice the speed, but half the moment of inertia. That means it has twice the energy. Because speed contributes more to energy because it's squared. So whereas the object 2 has 10 joules, this one's going to have 20 joules.
So what does...
That's right, right? That's the right answer?
Yeah.
Yeah.
So what does energy relate to? Like what are you multiplying by?
When I think of energy, kinetic energy is 1/2 I omega squared. Okay? Angular momentum is I omega. So if I have two objects with the same momentum, if one of them's going faster, that's okay, it can go faster, it'll just have a smaller moment of inertia, but it's going to have more energy because I have this omega is squared. So like if something has twice this, but half this of another object, then it's going to have twice this, 2 squared is 4, half this, half of 4 is 2. The energy is going to be increased by a factor of 2. That's a difficult question. Like every time I see it, I have to sit down and think through it. But it's a good skill for you to have. You've got good skills being able to do that. Mad skills. Dope skills. This is in the concept test. So if you're still wrapping your head around it, look back at the concept test. There were a couple questions regarding this. I don't think I've downloaded that yet. Let me make a note so you all have it. In fact, I'll go ahead and upload chapter 10 too, which for you online students, I know you haven't taken the OP quiz yet, but it'll be on there for you. Okay? I'll do that when I go back to my office. Mallory, is that okay?
So, last question. I get that like 2 squared, that's 4, and then 5 by half, that's 2.
Mm-hmm.
But then you have 5 by half again.
Oh, but no, this factor is just in the equation. We're just asking about how am I changing these variables? Because I have two objects with energy, right? Both of them have 1/2 I omega squared. One of them is twice the velocity, but half the moment of inertia. This one's going to have twice as much energy. Okay?
So coefficients that are already in the problem here are just messed up like this.
Right, they don't count. Because they're the same for both scenarios. It's tricky, I understand. Look back at the concept test. It'll be useful for that. Okay, what else? Yeah. Number 5 on this same one. Okay, so when you look at these, this one looks a lot like a Newton's second law problem, but it's not. It's actually a momentum problem. And part of that is that you'll be able to tell because the problems are all grouped together. So like all the momentum problems are together and all the Newton's torques problems are together. So that'll help you. But when you look at this one, the reason that you know that it's not a Newton's second law problem, that's what you do the sum of the torques is I alpha, is because there are no forces involved here. And so if you don't have any forces, then there's no need to apply Newton's second law. So, but I still have talk about the speed and the moments of inertia and all that business. So that would clue me in into thinking that, oh, this is a conservation of momentum problem. And so what's happening here is I say that Li is equal to Lf. The moment of inertia is initially 8, and it's initially rotating at 2 revolutions per second. So I omega, remember L is equal to I omega, 8 kilogram meter squared, times 2 revolutions per second. Now that's not SI units, but remember with angular momentum, that's okay, because the units cancel out anyway. And then I have 2 things that are going. I have one that's rotating counterclockwise, and then one that's rotating clockwise. So I have to actually add these 2 together. Plus the second object, which is going to be 16 kilogram meter squared, times 4 revolutions per second. But what? It's negative. Why is it negative? It's clockwise, right. Look, I left a little space there. That's awesome. So because it's clockwise, if you see counterclockwise, clockwise, remember what we said. Clockwise is negative, counterclockwise is positive. Keep that in mind, okay? And now this is going to equal to, these 2 objects, they come together. And now they're going to have a new moment of inertia that's going to be 8 plus 16. Because moments of inertia, they add up, just like Richard Pryor and the thing. You just add it up, right, to get the total moments of inertia times omega final. And so that's 16 minus 64. Is that minus 48? Is that right? Equals to 24 omega final. So it looks like omega final is 2 revolutions per second negative, which is clockwise. A. Chapter 8's tough. Right? There's a lot of little details that come into Chapter 8, and you have to get a lot of practice to be on top of them. I try not to let those trip you up as much as possible, but knowing the details is, that's what separates a B from an A C from a B. Okay. All right, what's next? Is that okay? Well, oh, that's this one. Manometer, this problem? Okay, you will have a manometer question. All right, you shouldn't be surprised by that. So in this question, I wanted to know the pressure P. I tell you that P naught is 1 atmosphere. And I want to know what P is. So remember, P is equal to P naught plus or minus rho GH. And so now I need to figure out, well, is it plus or minus? Is P bigger or smaller than P naught? What do y'all think? It's bigger, because it's pushing down more on this side and forcing the liquid up on this side. So P is bigger than P naught, so I'm going to use plus. P is equal to P naught plus rho GH. And so that's equal to 1 atmosphere. That's 1 times 10 to the 5th pascals, plus rho is mercury. Oh, I look at my table. I find that the density of mercury is 13,600 times 10 times H, which is 0.1 meters. And so that's 114,000 pascals, but that's equal to 1.1 atmospheres. That's on your equation sheet, the conversion factor, but 1 atmosphere is equal to 100,000 pascals, newtons per square meter. And so it's going to be B is the right answer. You will have one of those. It'll work. It'll be different numbers, of course, but it'll be pretty much identical to that one.
And then can we also show the hydraulic system?
Yeah, I'm sure there's one on here, because you'll certainly have one of those. Okay, so on this one was a little bit different from the one that we did in class, but it's really the same. It's really exactly the same. I have two pistons of the master cylinder and then the brake cylinder, or I think it's called the slave cylinder. Is that what it's called? The slave cylinder? Yeah. Anyway, so the master cylinder has an area of 2.4 square centimeters. This brake cylinder has an area of 9.6 square centimeters. Sort of looks smaller in the picture, but it's actually bigger. Because you want a bigger force, right? You're applying a bigger force to the brake. And then I say that the pressure on the first side is equal to the pressure on the second side. That's going to be the force that I apply, which is 16 newtons, divided by 2.4 square centimeters, is going to be equal to the force on the other side divided by 9.6. Look, though, if you don't want to go through this process, you just look at how the areas compare. I have a factor of 4 from this area to this area. My area increases by a factor of 4. That means my force is also going to increase by a factor of 4. So it was 16. 4 times 16 is 64. E is right answer. That came up on your OpenStax, by the way, the wine thing, where they had put the wine in a barrel or a big bottle. It's the same. It looks a little bit different, but it's really the same. I have a cork. I'm applying a force per unit area up top. I have a bigger area down at the bottom, so I get a bigger force per unit area. The pressures are the same, but the force is bigger on the bigger area. That was in the Chapter 9 OpenStax, which is due tomorrow night. Okay? All right, what else? Oh, while we're on brake systems, let's talk about that OpenStax with the brake system. Did y'all get that one right? No? It's not really a hydraulic system question. It's really a question of torques. I forget all the details of it, but you have the brake pedal right here. With your foot, you're applying a force. I think it was 100 newtons or 200 newtons or something like that. 100. You're applying 100 newtons at a certain distance. I think it was 0.2 meters. And then that also imparts another force. I think it was F1. And you have to F2. You know this off the top of your head? This is 0.04 meters. And so I have to balance my torques. That's going to be 100 newtons times 0.2 meters is equal to F2 times 0.04 meters. And I solve that for F2. It's a big force, right? Because, or no, it's a smaller force. The force gets smaller. Wait, no, I'm sorry. It gets bigger. Bigger by a factor of, I don't know, something, 5, 50 or something. Is it centimeters or meters?
I think it was 20 centimeters and 0.04 centimeters.
No, that would be 40 centimeters. It's like this long on your... It doesn't matter what the numbers are. But you solve for the force, and then you have to solve for the pressure inside the cylinder. And so once you find F2, the pressure is just F2 divided by the area of your cylinder. You have to calculate the area of your cylinder. Be careful because they give diameter in centimeters. You have to convert that to radius in meters and then find the area pi r squared. I know that's a lot of hoops to go through, and you won't have to do that for the test on Monday, but you do for the OpenStax. Okie dokie? What else, folks? I know there's a lot more stuff. I need questions. Alex? So 20 is, it talks about Young's modulus, so you know that's going to be the stress-strain thing. So it's just F over A is equal to the Young's modulus, delta L over L, And then it's really a matter of knowing what the various quantities are. So this 10 meters, that's its original length. That's delta L. That's L. This is delta L. Your units here are kind of funky. You got to get everything in the right units. So it's 10 meters. Delta L is 1 centimeter. You move that decimal place over 2 spots, so it's 0.01 meters. And then the force is 1,000 newtons. And then so the area, we need to know the cross-sectional area. The diameter is 0.02 meters, so the cross-sectional area will be pi times 0.01 squared. So I'm going to put that over here, pi 0.01 squared. And then we would solve that for y. I don't know what the answer is. Anybody know? Is it B? So when we solve that for y, 3.2 times 10 to the 9 pascals, if that's what the answer is. Okay? Pretty sure you have a, yes, you do have a question like that. And it's, you got to know what the question is. If you know how to do it, it's easy, but that's true for everything, right? If you know which equation applies, if you know what all the variables are, these don't require a whole lot of process. They just require knowing the variables. And again, you did have to solve for the area here, but I'll try to minimize that as much as possible because I know that takes time. Let's just sort of skim through, and y'all can holler out if you see something. This is a pretty good indicator of what your exam will be like. There's flow. This is chapter 8 stuff. Ooh. Okay, you're going to have one like number 7, frankly, because you have to find the net torque. Absolutely. Let me get rid of all this. Okay, so for number 7, I want to know the net torque about this point right here. And to find the net torque, I just add up the torques. First of all, identify the forces that don't give any torque at all. So this force, which is at a moment arm of 0, no torque at all. But both of these forces give a torque. Then you need to identify, is it clockwise or counterclockwise? This one causes it to rotate in this direction. So this one is clockwise. It's going to be a negative torque. I'll call this torque 1. And so it's going to be negative torque 1 plus torque 2. This one is torque 2. It causes a counterclockwise torque. Now be careful. It's not just because it points up that it's counterclockwise, because this one pointed up and it made a clockwise torque. You want to think about the axis of rotation. This one causes the object to rotate in this direction. But this force pulls up on this side, and it causes it to rotate in this direction. So don't try to think, oh, well, if it points up, it's clockwise or whatever. That doesn't work always. It depends which direction it causes it to rotate. I like to use my pencil, and then I can sort of think about, well, this force pulls up, and that causes it counterclockwise, and vice versa over here. If that helps you, that's great. So now we know the signs for the torques and how they add up. And so I say negative 20 times 2. That's the force times the length of the moment arm, 2 meters right here, plus 10, that's the force, times 2, that's the moment arm, times the sine of 30. And then what's the answer? 30? Was it negative 30? Yeah, so that's negative 30. Because it came out negative, it's going to be 30 Newton meters clockwise. You're definitely going to have to do that tomorrow, okay? Or Monday. Well, that's a good question. So what if it was over here, the axis of rotation? This one would cause a, what, clockwise? Yeah, it causes a clockwise torque, and this one also causes a clockwise. Let's just do that right quick. What if I have it right here? Then my net torque would be negative 20 times 4, because that's the distance to the axis of rotation, minus 5 times 2, because that's the distance to the axis of rotation. They're both negative because they're both clockwise. And so that's going to be negative 80 minus 10 minus 90 Newton meters. Okay, that's a good question. Now that also leads into number 8, and you'll have to do one like number 8 too, where I ask you some basic question about the kinematics, but that's actually where you're applying Newton's second law. You want to do this one too, Blair?
So in one of the tests, first question said it was rotating about the axis, and then the second problem was that question, but you assumed that it wasn't rotating, even though the first problem said it was rotating.
I don't remember that. If you can tell me the one it is, we can look at it. I doubt, I mean, I trust you, but I doubt that that would have happened. Okay, can I do number 8 while she's looking?
It is that.
No?
Yeah, well, it says, yeah, consider this figure of a rod rotating about the axis.
Okay.
So is it already moving? That was my question.
Oh, I see what you're saying. Yeah. So it's maybe a better way to say it is that it's allowed to rotate about that axis. Okay? All right, let's look at this next one. Don't worry about that. It's not that important. It's important. But, okay. Okay, so the bar in the previous problem, after 2 seconds of that torque acting on the rod, what is the rod's angular velocity? A couple of things you have to do here. First, you have to find I. And for a rod that's on your sheet, 1/12 mv squared, which is 1/12 of the mass, which is 3 times 4 squared. 3 times 6 is 48, so that's 4 kilogram meters squared. That's my moment of inertia. Then I say the sum of the torques, which I've already found to be negative 30, equals 4 times alpha. So alpha is 30 over 4. It's 15 over 2. That's minus 7.5 radians per second squared. And now I want to know the angular velocity. Omega is equal to alpha t. And this is where Blair's comment becomes important, that we're assuming that the initial angular velocity is 0, which I understand is not exactly clear. Okay, so omega is equal to alpha t. Alpha is minus 7.5. T is 2 seconds. 7.5 times 2 is 15. And the negative doesn't come up because it doesn't say anything about direction, so we're asking for the magnitude. Okay? What else? I can sort of skim down here. Particular questions, y'all? You haven't had a lot of time to dive into it, have you? Sorry. Opens, yeah. Mm-hmm. Probably one on this one. There's not. Oh, here we go. Number 24. And again, this is sort of like the Young's modulus bit, the stress and strain, that if you know the equation, you sort of know the variables, then there's not a lot of process to it. It's just picking out the variables. So I want to know the length of the beam on these hot days. Our change in length is equal to L naught alpha delta t. The change in length is going to be the original length, which is 25. This is steel. I think it's 11 times 10 to the minus 6. Is that right? For steel. And then delta T is 40 degrees Celsius. Anybody confirm that? Is that right for steel? Yeah, what are they? Okay, we'll just use the 11. See how it works out. And then that's equal to, anybody know what this is equal to? Looks like 0.011. Yeah, so 0.011 meters. So that's the change in length. It gets longer by that amount. It was originally 25 meters, so it's 25.011. I think. Oh. No, I'm sorry. That's on the equation sheet. Yeah. Those are different types of steel. They're slightly different linear expansion. I think I'll do linear expansion in organic lab. Is that right? Huh? Oh. All right. It's a good way to determine unknown materials. To look at their various physical properties, and that's one of their physical properties. Okay. What else, folks? OpenStax questions? Any of those giving y'all boogers? Too much to write. Is that all, folks? Okay. Listen, I'll be in early in the morning for a little while. If you need some time, I'm available then. But otherwise, shoot me an email, and then on Monday morning we can meet too. Okay? Here, send me an email. I can respond to a lot over email. Oh,